Do you hear me? No. Do you hear me? No? Do you hear me now? Is that okay? Hello? Maybe a bit higher. Do you hear me now? Still not? Okay, I'll speak louder. Okay, so first of all, I would like to thank the organizers for giving me the opportunity to speak here. It is an honor for me. And I also would like to thank them for organizing this conference in this beautiful place. Okay, and what I want to talk about today is joint work with Florian Schetz. So, and this is work in progress. Okay, at least one part of it is. So, what I want to talk, so the subject of my talk would be to do differentiation and integration. So, Lie theory, how do you go from infinitesimal to global, and the other way around for representations up to homotopy. So, representations up to homotopy is just the homotopy version of representations, and it turns out that if you want to do the usual constructions that you have for Lie algebras and Lie groups, for Lie groupoids and algebroids, you can carry them out usually in this context, and then you get analogs of the usual representations that have the right formal properties also in this context. And for instance, they behave in the expected way with respect to the deformations of the structures and with respect to the cohomology of the classifying space. So they really seem to be the right analogs that one might be interested in. So let me tell you the plan first. So my plan, so first I'll have to give you some definitions. So I'll tell you, explain a little bit the words in the title. Then I'll tell you how you can differentiate. And as an application of the differentiation procedure, I'll say something about, well, I'll give an application to the deformations of Lie brackets. And then I'll talk about integration. So here I will explain what it means to integrate, or in what sense one can integrate these things, because it's not necessarily the first guess I would have made. And then the last part is how to explicitly construct the integration using the theory of chance iterated integrals. So chance iterated integrals provide explicit formulas for constructing the integrations. Okay. Now let me start with at the beginning. Let me start by giving you some definitions. So these representations up to homotopy are really what you would imagine intuitively. Instead of having an action of something, say a group or a groupoid on a vector space, you have an action on a chain complex, and you want the multiplication to be compatible, the composition to be respected only up to higher homotopies. So it's somehow very intuitive. Let me give you some formulas. So the definition. So in the talk, G will be, say, a Lie groupoid over a manifold M all the time. And it will have a Lie algebroid A. So a definition is that a representation up to homotopy, which I will denote by this letter, of G is a graded vector bundle E over M together with a sequence of cochains So you have a bunch of of cochains, fk, one for each natural number, and this is a cochain on your, say, on your groupoid with values in endomorphisms in your vector bundle. So what this means, being a cochain, simply means that if you give f a sequence of composable arrows on G, then it will give you an endomorphism of E. And I want this to have a specific degree. I want it to have degree 1 minus k, so that the total degree is 1. So it's just a bunch of cochains, but they should satisfy one equation. They satisfy this twisting cochain equation, which I write here. So this tells you, maybe it doesn't tell you much in this generality. I'll try to do some low degree examples to convince you that they're really very simple. But intuitively, it tells you that this map that you assign to something of length k, when you take some sort of boundary of it, can be compared with the maps that you assign to the lower dimensional faces. That's intuitively what it means. Now, let's look at it in low degrees so that we really see that this is something very simple. And I want to use some, just because it somehow simplifies, well, or it becomes easy to read, I will usually denote f0 by delta. This is just a convention that I like. Now, let's look at what this equation means in the case k equals 0. It simply means that the first operator, f0, which I'm calling delta, when I do it twice, the commutator with itself, there's nothing here. So really, I get delta composed with delta is equal to 0. So it tells me that part of the structure I want my vector space, my vector bundle to have is that it is really a cochain complex. Now, if I look at the equation in degree 1, I'll see something else. I'll see that zero. So these two things commute, which means that you see the first, the F1, is a cochain which, when I put k equals 1, tells me that when I give it one element of my group, it gives me an endomorphism of degree 0. So that's typically what an action is. Actions are cochains of that degree. So this is telling me that the part of this structure, which is like an action, commutes with the differential. Oh, sorry, maybe I should have. No, it's okay. So it commutes with the differential. So it tells me, in particular, part of the structure is that for every G I have an action, which is an action by endomorphisms. Now, if I look at it in the next degree, I'll get some other simple equation. Which is this. And this also says something very intuitive. It tells me, well, usually I require these two things to be the same. That is saying that composition be preserved. But here this is telling me it's not quite preserved, but it's almost preserved. Because I have a hope these two maps are not quite the same, but they're homotopic. And I have a preferred way of choosing a homotopy between them, which is given by F2, which is part of the structure. So, and then if I do it, well, for k greater equal than 2, then I get higher analogs of these equations. So really, it's these equations are very intuitive. The point is that if you work in this category, well, if you allow this kind of representations, that you get many examples which have interesting properties. Okay, so this is at the global level. So what I want to talk about is about Lie theory, so there should be a corresponding object at the infinitesimal level. And I want to give you also the definition there. Okay. So this would be the global part. And then I'll tell you the infinitesimal part, and then we can see how these things compare to each other. So let's let's do the completely analogous definition on the infinitesimal side. So now a representation of the homotopy of a Lie algebroid A is exactly the same, a graded vector bundle E over M together with a sequence which I want to denote like this. Sorry, this is omega 2, omega 3, omega 4, and so on, which are as follows. Omega I is again, well, a cochain with values in endomorphisms of degree 1 minus k, which is just means section of this bundle. So these are the omega i's, but in the first degree, it's not quite a cochain, it is something like a connection. So nabla is an A connection. So this means that it is a rule that tells me how to differentiate sections of the vector bundle E in the direction of the sections of A. It's just the infinitesimal version of an action here. So this is an A connection. And this sequence should also satisfy some properties, and the properties are the Maurer-Quartan equation. So they should satisfy the infinitesimal version of the associativity condition that I wrote here, which is the Maurer-Quartan. Which is this one here. And if you look at this, if you just decompose these equations in low degree the way we did here, you will see that you get, just as in the global case, you get a very intuitive description of what this means. This simply means that you have a complex of vector spaces, and you have something that's like a connection in each of them, but it's not quite flat, but you can control the curvature. Yes. I mean, there is something that you, here it's a Lie algebra, so you're taking into account the smooth structure, but yeah. So if it was a Lie algebra, yes. I'm sorry? G was acting trivially. Yeah. Was acting trivially on M? Oh, G is a groupoid over M. So it's... Yes, so A is the Lie algebroid of the groupoid G. Mm-hmm. Right. So as I was saying, when you look at these equations in low degree, they're very intuitive as well. Okay, so this is probably all I want to say about the definitions. I want to say now a little bit about how you can first go from the global to the infinitesimal. So I want to do differentiation. And as usual, the differentiation is very easy and the integration is less easy. So I'll be very quick in the differentiation because everything really works the way one would expect. So first I just observed that these objects, there's a natural notion of morphisms between them, and then they form a category, and then not just a category, they actually form a differential graded category. That's sort of the natural structure that these spaces have. And what happens is that, well, actually say the proposition is that there is actually a differential graded functor which is given by differentiation that relates the infinitesimal at the global. So there is phi from the category of representations of G the category of representations of A, which is a DG functor, given by differentiation. So here everything is really what one would guess. And the way you construct this is more or less clear, right? So you have a bunch of cochains in your group, and you just differentiate the flow at all the slots in all the possible ways, and then you symmetrize, and then you get cochains at the infinitesimal level, and then you just need to see that these conditions go over to these conditions here. And then you need to see that it's compatible with morphisms, but everything really works the way one would guess. And maybe I should say that, well, these formulas for differentiating cochains I first saw in a paper by Weinstein and Xu. And, well, essentially the same formulas, when you apply them to these things and to morphisms, give you the functor. But I want to say just the fact that these formulas are iterated differentiation. So you just differentiate all the flows one after the other. So it's really an iterated differentiation. And I want to say it like that because going the other way around is an iterated integration. So it's really the inverse construction. Okay, so here everything works the way one would guess. But now the fact that this is not just a category, but a differential graded category, it's important because it tells you right away that it induces maps at the level of cohomology. So when you have one of these representations, there's a cohomology associated to it. And the fact that this functor preserves the differential graded structure immediately tells you for free that you get a map at the level of cohomologies. And then you can ask, well, is this map an isomorphism? Or when is it an isomorphism? And that's a question that's sort of very old. It was studied by Van Est in the case of Lie algebras and Lie groups and ordinary representations. And he gave the answer that depends on the topology of the Lie group. And it turns out, and then this result of Van Est was extended by Marius Kreinig to the case of Lie algebroids and groupoids for ordinary representations. And it turns out that exactly the same result is true for these representations at homotopy. So there's a version of this Van Est theorem which one can prove that says that the map, if the source fibers, so it's always a topological condition, it's exactly the same hypothesis as in the case of Lie groups, if the source fibers of G are n-connected, then and E is a sum from k equals A to B of E case. So I want to know what is the lowest degree in which E is non-trivial, it's non-zero. Then this map induced in cohomology, so the DG functor tells me that I have a map induced in cohomology from the cohomology associated to E to the cohomology associated to the corresponding infinitesimal representation. And it tells me that this is an isomorphism up to degree n plus A. So this is word by word the same result that Van Est got for Lie groups and Lie algebras. Now, this theorem is somehow not very clear that it's ever useful, but it actually has a rather concrete application. Sure. What is what? Oh, I'm just saying, so the functor psi takes a representation of G and gives me a representation of A. And the representation of A, I call it psi of E. Oh, as a vector bundle, it's the same. Yes, that's why I need to put a bound. That's why I'm sort of explicitly writing this thing. Well, I mean, if I wrote n here, you see, if I wrote, it depends on where it starts.
I mean, you're not in representation. It's not invariant under shape. So you cannot say that. You cannot simply regrade your concepts. Is that correct?
I'm not sure I understand your question. Can we discuss it later? Okay.
You can always assume that.
Sure, you can always assume that it starts at 0. And then the statement would be easier. Yeah. Okay. Okay, so as I was saying, so this has a more concrete application to the deformations of Lie brackets, which is which is the following result, which was conjectured by Kreinig and Mording. So it was the following. This conjecture by Kreinig and Mording. So it's theorem that if A is the Lie algebroid where G is proper and source 2 connected, then it is rigid. So then at least formally, the tangent space is the space of deformations, which is the second cohomology, differentiable cohomology group of A is 0. So you need 2 conditions here that I want to mention. The properness, of course, is the compactness condition that's going to tell you that there is some rigidity, and then you need some topological condition on the fibers of G. Now, this condition is exactly the same condition that we saw in Marius' talk in the rigidity of symplectic leaves. You see that you always need some. So this also shows up here. Now, the proof is really, I can say it in words, because it's just this is meant to be just a generalization of the fact that if you have a Lie algebra, which is the Lie algebra of simply connected compact Lie group, then the second cohomology with coefficients in the adjoint representation vanishes, which is what measures the deformations. And here, this proof depends only on the fact that, just as for the case of Lie algebras, the deformations of A are measured by the cohomology associated to one special representation up to homotopy, which is called the adjoint. And then if you observe this, and then you have some theorem of this kind, which allows you to compare the infinitesimal and the global, then you can reproduce word by word the proof you did for Lie groups in this setting. And then that will tell you some rigidity condition for group actions or for Poisson manifolds, things like that. And so it's really word by word once you know this, that you can just copy the proof of Lie algebras. Okay, so that's probably all I want to say about differentiation. So everything is very straightforward and works in the way one would guess. Now, I want to go in the other direction. So the other direction is integration. And this also works, but not in the most obvious way. So the first thing one would try, or at least the first thing I tried, is to try to go from rep of A to rep of G. Right? So this is the obvious guess, but it doesn't really work. At least I don't think it works. it turns out you need to do something a little bit different. And it's related to what we saw yesterday in Ezra Getzler's talk. So it's about the explicit point of view in integration in Lie theory. So you want to construct explicitly your Lie group in terms of the Lie algebra, and the way you do it is you look at some paths and you mod out by homotopies. So that specific point of view in Lie theory is somehow necessary for this construction. So, I mean, this way of integrating Lie algebra is probably very, very old, but it has been used recently by many people, many people in this conference, and I should mention some references that I've used to learn a bit about these things. So I should mention the work of Cattaneo and Felder on the Poisson sigma model, and the work of Freilich Fernandez on integration of Lie algebroids. I also should mention the work of Chen-Chang Su and the work of Ezra Getzler on integration of L-infinity algebras. And, well, André Enriquez wrote about it. And Pavel Cevera wrote a nice paper. Maybe I should also mention that the book by Hans Daustermatt and Kolk also sort of emphasizes on this point of view. I've also learned a lot from talking to Dimitri. Well, anyway, so there's many people. I'm just trying to say what the references I'm familiar with. And okay, so what is this point of view really? So the idea is quite simple. It's just that if you want to construct a Lie group, or let's say a Lie algebra, let me say it in a sentence. So the Lie groupoid integrating A is in an appropriate sense the fundamental groupoid of A, in the sense that you look at maps from, well, the tangent bundle of the interval to A, and you mod out by homotopies. And this happens in the category of Lie algebroids, or if you want, in the category of differential graded manifolds, or if you want, in the category of differential graded algebras. So let me write it like this. So this is just saying that integrating a Lie group or a Lie algebra is computing some fundamental groupoid just for a different type of manifold. Now, that's very good. Somehow intuitively, I think it's very satisfying. But then it turns out that if I had a representation of my thing here, A cannot really just truncate by all homotopies if I want to integrate representations. And you need to do something else. And the something else is, instead of just looking at your paths and modding out by homotopies, you can do is look at all homotopies at the same time. So you can look at the paths and then the homotopies between the homotopies, and try to keep track of all that information in some combinatorial structure. And so say your Lie algebroid was just a manifold, then you would be saying that instead of computing the fundamental groupoid, which is paths modulo homotopies, you just may remember all the homotopies, all the simplices you can map into your space. Mapping all the simplices into your space remembers the homotopy type of your space, because after all, you're just remembering everything about X. And it turns out that that space of simplices, or singular chains on your manifold has, well, it's not just a set, it has some algebraic structure. It has the structure of a simplicial set. So I want to think of this space of singular chains in a space. It may be a manifold, or it may be a digi-manifold in this case. But I want to take of this space of singular chains as some generalization of a groupoid, because it is a simplicial set. So let me denote it by, say, sing A for now, it's a sequence of spaces, one for each n, and this just maps from the tangent space to the k, well, maybe the n simplex to A. So this is in the category of Lie algebroids. So this is just looking at the space of all singular chains. So remembering all the homotopies. Now, these two objects seem to be objects of a very different nature a priori. But as we learned yesterday in Ezra Getzler's talk, they're really of very similar nature. And the way you can really compare them is through the nerve construction. So the nerve is just a functor that goes from the category cat of small categories to the category of simplicial sets. So it gives you a simplicial set for any category, and in particular it gives you a simplicial set for any groupoid. But once you think of a groupoid as a simplicial set, then you'll see that these two objects live in the same place. They're just objects of the same nature. And then that's the way I sort of want to think about it. So this is you just remember the one homotopy, and then instead of remember just the one homotopy, you remember all the homotopies. So instead of having pi 1, you have something that I would like to call pi infinity of A, which is just this simplicial set. And then you see that this is really just forgetting. If I forget a bit about a bunch of things about here, I'll get this one. Now, the reason I'm telling you this is because the integration doesn't really land here, it lands here. You really need to remember the space of all singular chains in order to be able to integrate. And the way you see this is very, somehow, the first observation is that these equations that I wrote here, the cocycle conditions, well, the bunch of cocycles and the relations between them, they do not depend at all on the fact that I have a groupoid. They can be expressed purely in terms of the structure of the nerve. So, and in fact, I think they appeared originally for singular chains, and they're called twisting cochains. So these equations I can express purely in terms of the simplicial structure. So in particular, it makes sense to have one such thing for this simplicial set. Let's try to see what it would mean, right, to have one such thing for such a simplicial set. Remember, I want to think of this as really being singular chains on some manifold. Just for every simplex, I have a map to my manifold. So I have a bunch of simplices. Now, what is this? So I had operators here, fk, which acted as sequences of composable arrows. Now, the sequences of composable arrows are precisely the k simplices in the simplicial set here, in the homotopy groupoid. These are precisely the k simplices in the nerve of the homotopy groupoid. So now the corresponding thing should be a bunch of operators fk, which act now not on sequences, but really on geometric simplices. So it means that for every simplex that I have into my manifold, I should get, there is an operator fk which acts on it, and it gives me an endomorphism of my vector bundle. Right? So it means something very simple. So it means for the space of zero cochains, that's just the space of points of my manifold, I have graded vector bundles. But now for each zero simplex, I have an endomorphism of degree -1. That's the structure of a chain complex in each fiber. But now if I have a path in my manifold, then I have a way to go from this point to that point. I have an endomorphism of chain complexes from the endomorphism that I have at this side to the endomorphism that I have at this side. And this is a map of chain complexes. But then if I have two different paths which are homotopic, they will not be generally inducing the same endomorphism. However, they satisfy some relations. And if I look at these relations from this sort of more geometric point of view, I'll write down, I'll try to draw them here. And they mean something simple. So this equation symbolically means that if I take the boundary of the map that I assign to a path in my space, this is 0, which is just saying that this path is really a chain map. Now, the way to think of this really, it's like a holonomy. So I have a path in my manifold and I have a holonomy assigned to this manifold. Now the difference is that I should be able to assign holonomies not just to paths, but to higher dimensional simplices. So the first condition on the holonomy is that it be a chain map. The second condition is this one for the two-dimensional cell, is that if I look at the boundary of the holonomy that I assign to the two-dimensional simplex, then this is really a homotopy between the holonomy that I assign to this, composed with the holonomy that I assign to this, minus the holonomy that I assign to this. So it's really telling me that this geometric homotopy between these two paths goes over to a homotopy between this composition and this map. So here you will see immediately that if I didn't have higher dimensional things, these two things would be equal, and then I would be able to factor through the homotopy classes of paths. But here, I cannot, because there are two-dimensional obstructions. Then there is the three-dimensional simplex, which satisfies an analogous condition. So if I have three-dimensional simplex here, and my vertices are ordered. So this three-dimensional simplex should get assigned a holonomy, and that's a map from this vertex to that vertex. And if I take its boundary, the boundary of that map, then I should be able to compare it with the holonomies assigned to the faces. And if you look at the simplex, you see that there are two types of faces. There are faces which contain the 0th and the 3rd vertex, like this one. Sorry, this is V2. So if I look at the holonomy assigned to this piece of triangle, I really go from where I have to go. So that's okay. So this one appears here, and also this one appears here. That's the back face of the simplex. But there are other faces like this one, which do not contain B3 and B0. And then what happens is really that what appears is really the cup product. It's the cup product of the front face and the back face, and I compose the holonomies, and the same thing happens here. So this is sort of the equation that I get that relates the homotopy assigned to this, and a simplex to the holonomies assigned to the faces of the simplex. And these are, well, higher order associativity conditions. So although this may seem a little bit abstract, when you write it like this, it's something also quite geometric. You think of it this way. No, for now I just think of it as a set. Sorry? Sorry? Yes. Mm-hmm. But you're right, there should be some continuity on F. But for now, I'm just thinking of it as a set. But it will be given, these holonomy maps will be given by some integrals of some differential forms, of course, and then you'll see that it really depends smoothly on the simplex, on the map. But for now, I just think of it as a set. Okay, so this was just the explanation of the sense in which these things will be integrated. So how much time do I have?
20 minutes.
Oh, okay, good. Right, so this is just sort of my third part of the plan, which was try to explain the sense in which one would be able to integrate. Now, I want to, well, state the result. Sort of the main result is that you can actually do it. So the result I'll state is really not the result I should state. The result I should state would be better, but I don't have we don't know how, well, we haven't proved that yet. But I'll state some partial result for now is that any E in rep infinity of A integrates to the integral of E in rep infinity of pi infinity of A. Of course, the result I really should state is that you get a differential graded functor from this category to this category. And it's clear that one can assign a map to every map, but we haven't really checked some of the properties. And so let me, what I would like to say is something else, but let me say this for now. So you can, at least the objects you can integrate well, like that. So I should now say something about the proof. And really, the proof is, in a sense, it's very old. It's really due to, I think, at least some instances of it, due to Chen in his work of iterated integrals. So Chen, this is in the 70s, so he wrote many papers on iterated integrals when he was studying the cohomology of loop spaces. And he wrote this, many papers on this, and in particular he realized that these iterated integrals that I'll say something about in a moment, they give you explicit formulas for writing holonomies of connections. So if you want to solve the differential equation for a holonomy, you can do it explicitly using these Chen's iterated integrals. And he realized that there are sort of higher dimensional versions of that. So in a sense, it's to Chen, but there's also a paper by Igusa where he expands on Chen work. This is from last year. And what we're doing is simply observing that more or less when you adapt Chen's construction for different, not just for a manifold, he always thought of manifolds, but if you do it for differential graded manifolds, at least special types of differential graded manifolds, what you get is really the Lie theory for these kind of things. You can integrate them. But
what way does Igusa extensions work?
So Igusa, right. So he wrote a paper which is called Parallel Transport for Superconnections. And he explains how the Chen's integrals give holonomies for, higher holonomies. But he doesn't really use the language of simplicial sets. And what he does is, at the end, so he explicitly writes all the formulas, but at the end, when he wants to interpret them, he says he wants to construct by hand a category such that these holonomies can be written as an A infinity functor from this category to something else. But I guess this is just because maybe he didn't want to use the language of simplicial sets. So he has to sort of by hand construct some category and then interpret the formulas as an A infinity functor. But I guess this is somehow more canonical. Now, I should also mention the work of other people. I should mention the work of Jonathan Bloch and Smith, where they wrote a paper which is called the Riemann-Hilbert correspondence for infinity local systems. So they also study this construction of Igusas in the case of a usual manifold. And what they show, although I don't understand the proof, is that a Riemann-Hilbert correspondence. So they claim that this, in the case of manifolds, this is there is really a DG functor, and that induces isomorphisms at the level of homotopy categories.
The tangents?
Yes, for a manifold, yes,
so
exactly.
By manifold, you mean the tangent?
Yeah, I mean that, exactly. So they study that case. And they prove a version of a Riemann-Hilbert correspondence in this for infinite local systems. Okay, so now I should tell you something about the proof. And the proof is really given explicitly. It's just a formula. So what does a proof of this theorem mean? It means that if I have a representation up to homotopy of a Lie algebroid, then I should construct a bunch of operators fk which assign holonomies to simplices. That's what it means. So I need to construct the operators fk which act on simplices. So suppose I have a k-dimensional simplex. Suppose I have a k-dimensional simplex on my Lie algebroid. It simply means a map like this. Then I should be able to assign a holonomy to it. Right? So I should be able, my fk should give me a map, an endomorphism of E of the right degree. So this can be written explicitly as an integral over a k minus 1 dimensional cube of some differential form, which is the pullback of some universal form on the path space, which is constructed by Chen's integral. So I'll explain what these things mean in a moment. But it's very explicit. So this is the map. I integrate some differential form over the simplex. And the claim is that all these holonomy satisfies these gluing conditions. Right, so maybe I should now explain what all these terms mean. And I'll try to draw a diagram to clarify this. Yeah. So let me draw a diagram like this. So I start with omega. I need to tell you what omega is. Omega is really just a differential form on the simplex with values in endomorphisms. So I'll tell you what this is in a moment. In any case, once you have omega, you can write 1 divided by 1 minus omega. Where does it live? It lives in the tensor algebra of this algebra of differential forms, tensor n of E. And maybe there's a shift in degree. So this is just a formal power series in this tensor algebra. But then there is the map. There is the map, which is really the key step, which is Chen's map, which from an element in this tensor algebra allows you to construct a differential form in the path space. So now you go to the differential form in the path space of the simplex with values in endomorphisms. And that's where, well, Chen of 1 divided by 1 minus omega lives. And then there's the other crucial step, which is somehow the most mysterious one, at least for, well, in some sense, which is that this I will explain in a moment, but this is a map that tells you out of an element here how to construct a form in the cube. And that's where the form I'm integrating lives. Sorry?
Even the whole collection of vedada can be understood as just any infinity morphism from Chevalier-Ellenberg algebra of the morphism of E just to the Derham algebra on the left. Because it's essentially for construction on an algebra, this is what Chen is doing, converting to infinity morphism.
I don't know, I can't say. Okay, so let me explain the pieces that go here. So first I need to tell you what omega is, right? So omega should be some differential form that I can associate to this map, right? So this map is a morphism of Lie algebroids. So remember that my starting data is some representation of the homotopy of my Lie algebroid A. Now, because this is a morphism of Lie algebroids, I can pull back this representation, and I get a representation of the homotopy of this Lie algebroid. Now, a representation of the homotopy of this Lie algebroid is just a flat superconnection. So this is a flat superconnection. And then I can trivialize the bundle because I'm over the simplex and write this superconnection as d minus omega. And that's the omega I have here. Now, so once I have a form with values in endomorphisms, this is just a formal step. This is just a formal power series. So this is okay. But now I need to describe this map. And this is Chen's map. And I will explain it, forget about the endomorphism for now, but it's somehow a very intuitive construction of Chen's. And
I'm sorry, that border where you flatten things, I didn't follow the argument.
Where?
What you said you had a flat superconnection.
Uh-huh.
You wrote flat connection on the board.
Oh, yeah, super.
And then you said you can now trivialize, but there are many trivializations.
Yeah, so you do it, it's convex.
Yeah.
And you have a connection?
But you don't have a flat connection, you have a flat superconnection.
Right, but you can do it along the lines. You have a point and you do...
Okay. So you picked so you're going to select a vertex, the initial vertex.
Yes. Mm-hmm.
So you use the initial vertex?
Yes.
And then you use the punctuation, the contraction.
Right.
Okay.
Mm-hmm. Right. Now, so now I want to explain this step here, which is Chen's map. So the idea of Chen's is, well, suppose you want to construct differential forms on the path space. So you consider the path space to a manifold, say. So you consider there's a canonical map that goes from the path space of a manifold times the simplex to m to the power k. M to the power k, well, here really the simplex appears as the configuration space of points in the interval, right? Here I would put different manifolds, I get different things, but here, because I'm looking at paths, which are maps from the interval, I get the configuration space of points, which is the simplex. And I have this evaluation map. Now that evaluation map induces a map at the level of differential forms. From forms in m to the power k to forms in the path space times the simplex. And then what Chen did was integrate over the simplex. I mean, there are some sign issues, but essentially to get a differential form in the path space. And the reason it's called iterator integrals is precisely because of this. You're integrating over T1, T2, T3. And this algebra lives inside. So if you do this composition, you get a map. And that's what I mean by the Chen map, which is this one here. So out of a bunch of differential forms in M, I can find a differential form in the path space. This is this step here. Now this step here is a bit, I don't have time to say much about it, but this is also constructed by Chen when he was studying the cohomology of loop spaces. So this construction here to the cohomology of the path space, it can be modified a little bit if you modify the evaluation map a little bit. And then instead of getting differential forms in the path space, you would get differential form in the loop space. And really, you'll see that if you embed this algebra as a subalgebra of differential forms here. And if you look at the de Rham differential here, it restricts to the Hochschild differential here. So that was studied very much by Chen and used to recover a theorem of Adams, proving that the Hochschild homology of differential forms is the cohomology of the loop space. Well, in any case, when he was studying the cohomology of the loop space, he at some point needed to compare the singular cohomology with the cubical cohomology. And in doing that, he constructed some maps from the cubes to the simplices. So she constructed some maps from the cubes to the simplices, which have some formal properties. Somehow they allow him to really compare these two constructions. Now, if you have such a map, you can look at its adjoint, which is a map from the k minus 1 dimensional cube to the path space in the simplex, right? By just moving one of the coordinates to the other side. It's just the adjoint. And this is the map that I'm using here, right? So I have a map from the path, from the cube to the path space, and I pull back by this map. Sorry, where is it? Here. So if I pull back by this map, instead of having a form in the path space, I'll have a form in the cube. And that's the one that I integrate. Now, the claim is that, well, this works. Now, 3. So now what is the logical structure of the proof? Well, first, why does it work? I guess the reason it works is because if you do this for a connection 1 form, just the usual connection 1 form, you do this construction, you look at the integral, and you see that you get the explicit solution for the parallel transport equation. And here you're doing the same things, but for higher dimensional things, so it's maybe not so strange. Well, although it was Chen's idea. Now, what is the logical structure of the proof now? The logical structure is quite simple. You see, this is a flat. I said that this is a representation up to homotopy, so you have this Maurer-Cartan equation. And when you pull it back, you'll see that this omega satisfies the Maurer-Cartan equation. That's the infinitesimal condition that we imposed. So the fact that omega satisfies the Maurer-Cartan equation here tells me that this formal power series will be closed in this complex, in this bar complex. So this has an internal differential and a differential that's given by multiplication. And the fact that this satisfies Maurer-Cartan tells me that this is closed. Now, Chen's map is not quite closed, but it is almost closed. So it tells me Chen's map does not quite commute with the differentials, but it has some boundary terms. Now, these boundary terms are precisely the ones that are responsible for the holonomy in the top dimensional phase. So this is sort of this side of the equation. And then the other side of the equation I just get by applying Stokes' theorem and integrating over the 2k minus 1 dimensional phases. And these 2k minus 1 dimensional phases are these 2k minus 1 phases here. Right? So they come from the 2k phases that a cube has. Now, the reason that there are two different types of holonomies here, some depend on the cup product and some don't, reflects the fact that Chen's map behaves differently with respect to front phases and with respect to back phases. So it's not symmetric. That's why there's sort of things which are non-symmetric in this construction. Yeah, so that's the logical. That's sort of that are all the steps into proof. Maybe I would like to say. So I mean, you can play this game with. The point is that there are many representations like this which allow you to play this game for many things, right? So if you do it for manifolds already, it's quite interesting. Also for the algebra, it's quite interesting. But maybe the case that I'm more interested in is the case of Poisson manifolds, because in this case, the simplices, the things that you want to assign holonomies to, are the fields of the Poisson sigma model. So I would be. I cannot really say anything about it, but I would be very interested in seeing the relationship, if there is any. Thank you for listening.